Pressures in the body may be measured either through a fluid-filled catheter connected to an external transducer or with a transducer mounted at the tip of the catheter. Frequency response is an excellent indicator of how accurately each of these systems detects pressures in the cardiovascular system for reproduction by hemodynamic monitors. This demonstration intends to describe the differences between external transducer systems with fluid-filled catheters and Millar catheter-tip pressure transducers. Therefore, to understand this difference, we should first review those factors which affect fluid-filled catheters and their frequency response. The fluid in the catheter, because of its length and weight, limits the frequency response of the external transducer system. Four major interrelated factors that control the amount of distortion are catheter stiffness, catheter length, catheter diameter, and trapped air bubbles. The degree of stiffness or compliance of a catheter determines its ability to transmit different components of a pressure waveform. Energy is lost due to the slight expansion of the compliant catheter, which in turn causes an increase in the amount of fluid that must be moved in the catheter during a pulse. Therefore, the stiffer the catheter, the better the frequency response. As the length of the catheter increases, the amount of fluid in the catheter increases, and greater energy is needed to transmit the pressure waveform. In general, the longer the catheter, the poorer the frequency response. The lumen diameter of the catheter should be large enough to allow the fluid in the catheter to move freely and to accurately displace the diaphragm of the external transducer. The larger the lumen, the better the frequency response. Air bubbles anywhere in the system can greatly reduce the system frequency response. This can result in a reduced amplitude or damped pressure signal. The combination of these elements affects a fluid-filled catheter's ability to accurately transmit blood pressure signals to an external blood pressure transducer. The next element of significance to affect the accuracy of pressure measurement in a fluid-filled catheter system is the external pressure transducer. It should have a high natural frequency, low volume displacement, and a structure that facilitates the removal or elimination of any trapped air bubbles within the fluid system. The external pressure transducer must be carefully placed to approximate the position of the tip of the catheter within the body. If the transducer is not positioned exactly, then the hydrostatic pressure differential can result in inaccurate pressure readings. Since the relative position of the external pressure transducer and the tip of the catheter must be estimated, it is logical to assume that some error will occur in all fluid-filled systems. While there are other characteristics in fluid-filled catheter systems that can cause error, these areas are the most significant. What you will see in this demonstration is that all of these undesirable characteristics of fluid-filled systems and the resultant inaccurate information can be eliminated with Millar catheter-tip pressure transducers. Since the Millar catheter-tip pressure transducer measures pressure at the source and does not require fluid as the means of signal transmission, the accuracy of the pressure signals is assured. This demonstration illustrates the difference in recording capabilities using a Millar catheter-tip pressure transducer and a conventional fluid-filled catheter with an external transducer. Let's first look at the components of our setup. Here we have a fluid-filled column in which both the high-fidelity catheter-tip pressure transducer and the fluid-filled catheter are inserted. In this fluid-filled column, we can generate a variety of pressure waveforms by moving a diaphragm up and down in response to an electrical signal that is supplied by a multifunction pressure generator. This multifunction pressure generator can produce sine, square, or triangular waveforms at frequencies corresponding to 0.2 beats per second to 200 beats per second. It also has the capability to reproduce other pressure waveforms from an auxiliary input. The catheter tip transducer is connected to a Millar transducer control unit and is in turn connected to the first or top channel on a dual trace oscilloscope. The fluid-filled catheter and its external pressure transducer is connected to another Millar transducer control unit and is represented on the second or lower channel on the oscilloscope. As you can see, the pressure signals being reproduced on the oscilloscope are those pressures that are being generated in the fluid column. To show that these are indeed pressure signals, let's remove this stopcock and open the pressure chamber to atmospheric pressure. Notice that both traces are now flat and that no pressure is being generated in the chamber. We replace the stopcock and the pressure waveform reappears on both traces. This shows that the display is not just an electrical simulation but a true demonstration of pressure reproduction. Measurements made with external transducers are extremely susceptible to movement artifact caused by the inertia of the fluid in the catheter connecting the transducer to the patient. Such movement artifacts can appear in the form of catheter whip, where the tip of the catheter rhythmically moves with each heartbeat, or as random extraneous signals caused by patient movement or movement of the external tubing system. As you can see, we are tapping the fluid-filled catheter and we get a lot of vibration on the lower trace of the oscilloscope. Now let's tap the Millar catheter. Notice that there is no additional artifact or vibration produced, and that artifacts such as catheter whip are totally eliminated with the use of high-fidelity catheter-tip pressure transducers. Let's now demonstrate the frequency response of both the fluid-filled catheter system and the high-fidelity catheter system. In order to accurately reproduce all of the components of a blood pressure waveform, both your pressure transducer and your catheter need to have the ability to accurately respond to frequencies of at least 10 times that of the basic frequency of the heart. For example, a heart rate of 60 beats per minute, or 1 beat per second, would require a flat frequency response to 10 cycles per second, while a heart rate of 180 beats per minute, or 3 per second, would require a flat frequency response to 30 cycles per second. Ill patients with fast heart rates could require an even higher frequency response to accurately reproduce all the components of irregular waveforms. With the MPG signal generator's frequency range switch set on the ×10 position and the function selector in the sine wave mode, we will scan from 2 beats per second to 100 beats per second and then store the information on the scope. You'll notice that the top trace, which is the high-fidelity transducer measuring pressure at the source, has a flat response over the entire range to 100 beats per second, whereas the external transducer on the bottom trace, measuring pressure through the fluid-filled catheter, starts showing a higher amplitude and phase distortion at about 10 beats per second. Also, notice that eventually, at peak resonance, the amplitude is several times the original amplitude. This characteristic of fluid-filled catheters causes considerable distortion and inaccuracies in the pressures being recorded from the patient. Now let's show how resonance can affect a square waveform, which is similar to the ventricular waveforms that you are more familiar seeing. We reduce the frequency to about 1 beat per second, simulating a slow heart rate of 60 beats per minute, and set the function selector in the square wave mode. We've increased the sweep on our scope, and we will now store the signals. Notice the Millar high-fidelity transducer has reproduced the square wave exceptionally well, whereas the results from the fluid-filled catheter on the lower trace are somewhat different. After the high-frequency transition point, there is considerable overshoot and oscillation or ringing. These artifacts are characteristic of a fluid-filled catheter system and will vary with the type of tubing used, the length of the tubing, the elasticity of the system, the type of transducer used, and with the amount of air in the system, often in the form of microbubbles. One of the common problems in using a fluid-filled system for monitoring blood pressure is that of air bubbles in the line. Normally, there are one or more stopcocks or manifolds in place where hidden air bubbles can remain trapped. Here we have the ideal situation. A fluid-filled catheter coming out to a transducer and no complex manifold involved. To show the effect of an air bubble on the signal produced by the fluid-filled catheter, let's introduce a small bubble into the system. This is a typical air bubble that you could find in a stopcock in your own facility. Let's now examine the scope. Notice that the amount of overshoot has been reduced. The frequency of oscillation or ringing has slowed down, and the overall waveform rendered quite different from the true waveform as reproduced on the upper channel. Even the steepness of the rise and fall of the waveform has been changed dramatically, and the derivative of the pressure waveform, or dP dt, has been decreased considerably. In order to quantify what these distortions might mean in the interpretation of a patient's blood pressure, let us assume that systolic pressure, located on the top portion of the high-fidelity waveform, is at 100 millimeters of mercury, and the bottom of the tracing, or diastolic pressure, is at 0 millimeters of mercury. However, on the lower waveform, at the same calibration, the patient appears to have a systolic blood pressure of 150 millimeters of mercury instead of 100. And his diastolic pressure indicates a peak negative value of minus 50 millimeters of mercury. A patient monitor, which can only interpret from the electrical signal applied to it, would indicate that this patient had a systolic pressure of 150 millimeters of mercury and a diastolic pressure of minus 50 millimeters of mercury, and might very well indicate that the patient needed medication that was really not necessary. These problems caused by air bubbles in a fluid system are totally eliminated by the use of a Millar catheter-tip pressure transducer, which measures pressure at the source, not after the signal has traveled through the elaborate fluid coupling system required with external transducers. Let's now flush the system and remove the air bubble. Notice that the resonant peaks have increased, as well as the resonant frequency and the value for dP dt. However, with the increase in the size of the peaks, a patient monitor would indicate that systolic pressure had increased and diastolic pressure was even more negative than it was with the air bubble. We've taken a pressure waveform from a patient in the cath lab, digitized it, and put it on an electronic memory chip. In turn, we are able to play back the signal through the waveform generator so that the original pressure wave is being duplicated in the pressure chamber. We can assume this to be the heart of a patient from which that pressure waveform is being generated. You can immediately see the dramatic differences between the two waveforms as they are being reproduced. Notice that the rising phase of the waveform is steeper with the fluid-filled system, and that in this case a dP dt reading would be erroneously high. The whole contour of the waveform is different. Now let's once again introduce an air bubble into the system. Notice how we've lost all of the fine details of the waveform, and there is a very evident time delay. The start of the waveform is here on this trace, but it is delayed on the lower waveform. The shallower rise of the wave front would provide a dP dt reading erroneously low. Again, let's remove our air bubble and we'll see now whether we indeed have a good reproduction. Even at best, this is not a good reproduction of the waveform by the fluid-filled catheter system. One of the other things to notice as a difference between the internal and the external transducers is that it is very critical where you place the external pressure transducer with respect to the patient. We can change the patient's indicated blood pressure by 10 to 20 millimeters of mercury just by raising or lowering the transducer. As it is raised, it looks as though the blood pressure is decreased. Conversely, if you have a fluid-filled catheter in a patient and he sits up, it will appear as though his blood pressure has increased by 10 to 20 millimeters of mercury because of the height difference between the tip of the catheter and the external transducer. This problem is also eliminated by the use of the Millar catheter-tip pressure transducer. No matter where the patient or source moves, the high-fidelity transducer will continually provide accurate blood pressure measurements. We feel that the best test for a pressure measurement system is its ability to produce consistently accurate pressure measurements. When you use our catheter-tip pressure transducers, we feel sure that you'll have a transducer system that will pass this test and give you the accurate results you require time after time. Since 1971, Millar Instruments Incorporated has been a pioneer in the development of catheter-tip pressure transducers for medical applications. Our goal has been, and continues to be, to provide you, the user, with the most accurate means of measuring pressures. We began the development of the Millar Micro-Tip catheter pressure transducer because we were concerned about the well-documented problems and errors associated with fluid-filled measurement systems. As a result, Millar catheter-tip pressure transducers are the highest quality, most technologically advanced, and most accurate devices available for measuring physiological pressures. Physicians and researchers in hospitals and research facilities around the world attest to the superiority of Millar Micro-Tip catheter pressure transducers.